A warm greetings to one and all. In this session, let's learn about formulating problems. Problem formulation is creating a model of a problem using mathematical or a logical representation. Examples are representing a puzzle game, maze game, a chess game as a set of states, actions, and goals. Core concept of problem formulation is abstraction. Abstraction means removing unnecessary details and keeping only the essential parts. It is mainly used to simplify the complex problems and make them easier to solve. Example for abstraction is a sliding puzzle with tiles. Here, the real details like tile color, material, or frictions are not important. So this is the example for sliding puzzle. We didn't consider the real details like colors, materials, friction and all, but still the gaming concepts which represents the 8 tiles, 1 to 8 tiles, one blank space is being given here. Let's consider the abstract model for 8 puzzle game. So it represents a puzzle as a grid with numbered tiles and a blank space. So we can see here we have 8 tiles, 1, 2, 3, 4, 5, 6, 7 and 8 tiles with one blank space. It mainly focuses only on tile positions and allow moves, namely up, down, left, and right. The goal is to reach the specific tile arrangement, that is from initial state to goal state. In short, abstraction simplifies the puzzle by ignoring irrelevant details like tile color, physical properties, and focusing on the important aspects like tile position and movement of the tiles. Let's learn about formulating problem using state space method. The first step is to identify the problem. So here we need to ask questions in order to understand the problem. Next, we need to define the type, method, and the necessary information for solving the problem. Second step is to specify the problem clearly. So here we should be precise about the goal by considering the limitations and criteria which are required to solve the problems. The third step is to analyze and represent the problem. So here we can use diagrams and descriptions in order to analyze and represent the problem. Normally in AI, problems are represented using state space diagrams. Fourth step is state space representation. So here a problem is broken into different states. Each state represents the available information. Actions or operators are applied in order to move from one state to another state in the state space. The process continues until the final goal state is reached. So this method of problem solving is called as state space method. Now let's learn about steps involved in formulating the problems. The first step is problem identification and problem definition. So this is the starting point where the problem is identified and clearly defined. So it has few key questions to address. The first one is what is to be solved. So here we clearly outline the goal or objective of our problem. The next is what are the initial conditions. So here we can specify the starting point or known facts about the problem. The next key question is what is the specification of achievable objectives. So here we need to determine the desired outcome or success criteria. The next question is what are the conditions that would arise from the action. So we have to consider the possible effects or results of each actions taken during the problem solving. The second step is problem space. It represents the collection of all possible states and paths that can be explored to solve the problem. It includes the initial state, intermediate state, that is, it represents the partial progress towards the goal, and finally the goal state, which represents that the objective is achieved or not. Third step is task knowledge. It involves the information and rules and regulations which is required to solve the problem. The examples are rules which is required in order to transition from one state to another state. the constraint which is to be followed in order to reach the desired goal state. And we should have some specific domain knowledge which is relevant to the task. Fourth step is state space. State space is a representation of all possible configurations of a problem at any point of time. It visualizes as a network or a graph where node represents the states and edges represents the action or transitions. Finally, it is a goal state. That is, the search for a solution involves navigating through this state space to find a path from initial state to the goal state. So these are the steps involved in formulating the problems. A well-defined problem in AI can be described by the following key components. The first point is initial state, that is the starting point or configuration of the problem. The next one is goal state. Here, this represents the desired outcome or solution which is to be achieved. Third one is action or operations. That is the possible moves or operations that can change from one state to another state. Fourth one is state space. That is the set of all possible states that can be reached by applying the actions. Fifth one is transition model. That is the relationship between state and action, showing how one state can be reached from another state. Next is goal state. In order to check whether the new state, that is the current state, matches with the goal state or not. Next one is path cost. It is optional. That is the cost associated with each action or a path is called as path cost. Finally, constraint. It is also optional. That is the rules or limitations that must be followed during the problem solving. So hope you are clear in well-defined problem. Let's have an example for formulating the problem. A well-defined problem in AI can be described by the following key components for puzzle problem. The first component is initial state. Here, the 2 by 2 grid is configured with the initial values 1, 2, 3, and a blank space. The next comes goal state. Here, the 2 by 2 grid is configured with the values as 2, blank space, 1, and 3. The next component is actions or operations. Here, the possible moves or operations that can change the state is called as actions or operators. The possible actions are towards moving left side and moving towards right side, moving towards upwards and moving towards downwards. The next component is transition model. The relationship between these states and actions are represented here. That is, showing how one state can be reached from another state. So in this example, from initial state S0, the blank space moves left by swapping with 3 and reaches the state S1, which is called as transition from state S0 to S1. The next component is state space. The set of all possible states that can be reached by applying action is represented as state space. Let's have an example here. Here, the blank space starts at the bottom right position and the state is represented as initial state S0, which is already given in a problem formulation. The blank space moves left by swapping with 3 and reaches the state S1. So now we need to check the state S1 with the goal state, whether it is matching or not. No, it is not matched. So now the blank space is moved towards upwards and swapped with 1 and reaches the state S2. Now the state is again compared with the goal state. No, it is not matched. So again, the blank space is moved right and swapped with 2 and reaches the state S3. So now we have to check with the goal state. Yes, it is matched now. So we have now reached the goal state from the initial state. So this is called as state space. If a problem can be solved in many ways, so there can be n number of state space for a single problem space. The next component is goal test. So we need to check whether the new state matches with the goal state or not. So that checking is called as goal test. The next component is path cost, which is optional. The cost associated with each action or path. So in our example, the path cost is 3 since we have 3 moves to reach the goal. The next component is constraint. It is also optional. Here, the set of rules or limitations that must be followed during our problem solving is being given here. For our example, the moves must stay inside the 2 by 2 grid. The blank space can move only left, right, up, or downwards. And a tile moves only if the blank space is next to it. And we cannot create or remove the tiles in our problem space. So hope you're clear in formulating a problem with this puzzle problem. Thank you all.